All right, what we're going to do now is we're going to look to see what we can do with power series once we have them. Okay, we can use them to create new power series. So actually one of the famous ones that we're going to play around with, at least in this particular section, is the geometric series, which is 1 over 1 minus x, which is just the sum of the powers of x, but it converges only when the absolute value of x is less than 1. What we can do is we can manipulate this to find power series representation for other functions. So as an example, find a power series representation for the function 1 over x plus 10. Well, this doesn't quite look like that, except for the fact that all the action is down here in the denominator. So what I'm first going to do is switch the order of these two, the x and the 10, and turn it into a subtraction in the denominator. So 1 over x plus 10 becomes 1 over 10 minus the opposite of x. That seems kind of silly because we want 1 minus some quantity. So we factor out 1/10. If I factor out 1/10, that means we're going to divide each term in the denominator by 10, so we get 1 minus the opposite of x over 10. Now this has the form of a geometric series. 1 over 1 minus anything is 1, plus that anything squared, and so on. So 1 over 1 minus the opposite of x over 10 is going to be 1 plus the opposite of x over 10 plus the opposite of x over 10 squared, and so on. So we have the 1/10 that was hanging out here originally, 1 minus or plus the opposite of x over 10, the opposite of x over 10 squared, the opposite of x over 10 cubed would be next. We're just following this particular form because this is 1 over 1 minus a number. Okay. Now, if I want to write this as a nice, concise sum using summation notation, notice that we have a negative 1/10 raised to a power each time. So here it's negative 1/10 times x. Negative 1/10 squared times x squared. The next will be negative 1/10 cubed times x cubed. And so when we end up, I'll just put the negative 1 in the numerator. I'll have 10 to the nth in the denominator, but when I multiply by the 10 that's out here, it becomes 10 to the n plus 1 times x to the nth. Just putting in a nice, concise summation. Okay, well, what else can we do with these? Well, we can actually differentiate or integrate these things term by term. And it turns out that if we know the radius of convergence for one of our series, when I integrate it, the radius of convergence won't change. When I differentiate it, the radius of convergence will stay the same. Now, what may end up happening is we may change the interval of convergence. So I might have a series which converges from -5 to +5, not including either endpoint. But when I integrate or differentiate, maybe I get one of the endpoints or neither of the or both the endpoints. Okay? So let's look at an example of this. Not really a problem as it's stated, just an application of this. Let's take our geometric series and differentiate it. Well, using the chain rule, that's 1 minus x to the -1. Bring the -1 down, lower the power by 1. Multiply by the derivative of the inside, which is -1, which will boom, reduce with that, or combine with that to give us +1. So we now have a new expression. If I differentiate the left side of my geometric series formula, I should be able to differentiate the right side and figure out the geometric series for this. Well, the right side of the geometric series was 1 plus x squared, and so on. Derivative of 1 is 0, derivative of x is 1, 2x, 3x squared, and so on. Okay? So this quantity, 1 over 1 minus x squared, is 1 plus 2x plus 3x squared. That's its power series representation. Now, if we want to be fancy, write it as a sum. There are a couple of ways I can do this. One is that I can see that my coefficients go 1, 2, 3, and so I can say n starts at 1, and I'm going to have the coefficient n, raise it to the power n minus 1. Well, that's exactly the formula for the derivative of the x to the nth power. However, we often like to write our series so that our index starts at 0. That's what n is. Our n is called our index. So that's 1 times x to the 0th, 2 times x to the 1st, 3 times x squared. So if I have x to the n, notice that the coefficient of x to the n is always 1 greater than the power. So that's another way we could write that. So now we combine these. 1 over 1 minus x squared is equal to that. That's the power series representation for that. Okay. Well, what about integration? We haven't talked about integration. Well, we're going to do something. We want to find a power series representation for the inverse tangent of x. Now that seems rather vague, rather open-ended. How am I going to do this? So I want to start thinking about things that I know about the inverse tangent of x, one of which is that the derivative of the inverse tangent of x is 1 over 1 plus x squared, which looks somewhat similar to the geometric series. Geometric series is 1 over 1 minus x, so I'm going to take this positive and change it into a negative, 1 over 1 minus the opposite of x squared. And remember the form. Whatever I was subtracting from 1 in the denominator, it was 1 plus that thing squared, plus that thing cubed, and so on. So I'm going to end up with 1 plus the opposite of x squared, or that is 1 minus x squared, plus the opposite of x squared squared, which gives us positive x to the fourth, minus x to the sixth, and so on. Well, remember, this is the derivative of inverse tangent of x, so to find a power series representation for the inverse tangent of x, I integrate both sides. Well, this is pretty easy to do. The left side is the inverse tangent of x, the right side is going to be x. 1 more than 2 is x cubed, we divide by the new exponent 3, x to the 5th divided by 5, x to the 7th divided by 7, and so on. Now we need a constant because these might not be identical. They might differ by a constant. But the inverse tangent of 0 is 0. All we need to do is check one particular x value, and that will give us what the constant is. The inverse tangent of 0 is 0. If x is 0 over here, we get 0. 0 plus c is going to be equal to 0, so it turns out that c is equal to 0. So the inverse tangent of x is x minus x cubed over 3 plus x to the 5th over 5, and so on. Which, if we want to be fancy and write it in summation notation, notice our signs alternate. We start with a positive, so we're going to end up with negative 1 to the nth in the numerator. Our denominators are the odd numbers, 1, 3, 5, 7. If n is 0, 2n plus 1 is going to be 1. If n is 1, 2n plus 1 is 3. If n is 2, 2n plus 1 is 5, and so forth. And so we get exactly the denominators we want. Our exponent matches our denominators. Now, that's wonderful. But there's something really interesting about this. The inverse tangent of x is related to pi, right? Turns out the inverse tangent of 1 is pi over 4, right? The tangent of pi over 4 is equal to 1. So that means that pi over 4 is this series with x replaced by 1. 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, and so forth. It's kind of an interesting way of looking at things. Now, we would really need to check convergence. Does it converge? Because remember, this guy is only going to converge with a radius of 1. That's at one of the endpoints. X equals 1 is at one of the endpoints. But this is an alternating series, is it not? We have 1 and 1/3, 1/5, 1/7. That's a decreasing sequence which approaches 0. So it's an alternating series. It passes the alternating series test, so it does converge. And in fact, it converges to pi over 4.